Good day everyone, I'm Victor Salanga and my project is a low-cost portable wideband RF spectrum analyzer via downconversion mixer. What is spectrum monitoring? The spectrum monitoring is a powerful tool used by many people such as engineers, RF analysts, and even telecom operators to inspect different signals whether they are functioning as they should or not. Why use spectrum monitoring? Well, through spectrum monitoring, you can characterize every behavior and every aspect of the signal you are watching. Also, through it, you can detect if someone from somewhere is performing illegal or illicit transmissions. The signals being analyzed are divided into bands which are shown in this table. The scope of the project will be within these bands which are mainly used for mobile, Wi-Fi, GPS, 4G, and television broadcasting. In order to detect the signals, an equipment called spectrum analyzer will be used. There are different types of it and the one shown here is the most commonly used, which is the super heterodyne method. There are different handheld spectrum analyzers available in the market. Some of them are listed in here with their frequency range and cost. As you can see, the wider the frequency range, the more expensive it gets. Here's the statement of the problem. Spectrum sensing is the process of monitoring frequencies defined by a specific bandwidth to detect and identify segments being used. The spectrum analyzer is the device used to measure the signals which can be low cost but has limited frequency range or wider range but it is costly. The goal of this project is to design and develop a device that has a wider range of supported frequencies yet still being affordable. Here are the objectives wherein the goal is to design and develop an affordable portable spectrum analyzer with extended bandwidth using mixer integration, quantify its accuracy taking into consideration the conversion losses, noise figure, and spurious, and evaluate the device's sensitivity for different frequency. Here's the general setup of our mixer, wherein the RF's input signal will be introduced to a local oscillator to produce the IF output signal. Here's its computation, wherein we have a function for the RF voltage and LO voltage. Multiply them to produce the IF voltage, wherein the product is a cosine function of the sum and difference of their frequencies multiplied to half the product of their amplitudes. The difference represents the down conversion process while the sum represents the up conversion. Since we are to implement a down conversion, the equation reduces to number 5 which will then be the function of our IF voltage. Here are the two mixer operations, which is the down conversion and the up conversion. The down conversion is the product of RF and LO to produce the IF, while the up conversion is the product of IF and LO to produce the RF. The one that will be used for this project is the down conversion. This section will explain the circuit diagram of the proposed device. The device consists of an antenna, an RF switch, a mixer, two receivers, and a controller. The input signal that ranges from 240 MHz to 4000 MHz will enter the SMA connector that will serve as the antenna. It will then pass through an SPDT or the single-pole double-throw RF switch that will trigger a certain state depending on the frequency of the input signal. Here's the schematic diagram of the proposed device. As what can be seen in the figure, the schematic has the two receiver ICs with their corresponding passive components and included also is a voltage regulator. This, together with the mixer schematic diagram that will be shown later, are connected to the 2.54 pitch pin header located on the leftmost corner. Here is a closer look at the voltage regulator and pin header. This is the SI4313, the receiver that is directly connected to the RF switch that will be shown later. It is the pass-through receiver that will receive the signal from 240 MHz to 960 MHz. This is the SI4362, the receiver that is connected to the mixer and will receive the signal from 961 MHz to 4 GHz, after it has been done converted to 868 MHz. Here's the schematic diagram of the mixer RFC5072A. It is connected to the RF switch SKY13286-359LF and will receive the signal from 961 MHz to 4 GHz. It also has transmission line balance which are essential for proper mixing operations. Here's the RF switch that is connected to the 1:1 balun of the mixer, which is the TCM1-43X+. Here's the 4:1 balun of the mixer, which is the TC4-13TX+. Here's the loop filter of the mixer. It is suitable for frequency reference from 26 MHz to 52 MHz as it gives the lowest possible integrated phase noise within the system. RF and microwave circuits behave differently than normal ones, especially at higher frequencies, so proper consideration should be observed during the designing of the schematic and PCB layout of the proposed spectrum analyzer. These are accounting for stray impedances produced in creating traces for the PCB layout, proper materials and types of passive components choosing, and efficient yet effective positioning and placement. This in turn will theoretically minimize losses and maintain its reliability. Here's the partial PCB layout of the proposed RF spectrum analyzer. Here's the partial PCB layout of the proposed RF spectrum analyzer in 3D. And here's the partial PCB layout of the proposed RF spectrum analyzer in board planning mode. Here's the Microstrip impedance calculator used in order to determine the proper dimensions and characteristic of the transmission lines within the layout of the device. Here's the bill of materials generated for components procurement. Since the device have not been fabricated due to the global pandemic crisis, the project transitioned into simulation. Here's the schematic diagram of the proposed device. It still has the two essential blocks that will be used originally in the actual device, such as the RF switch, the mixer, and the two receivers. The RF switch has two states that triggers the designated paths depending on the input signal frequency. Here's the S parameter S11 and S22 spectrum of the wideband receiver that is directly connected to the RF switch. Here's the S parameter S11 and S22 spectrum of the mixer connected to the second wideband receiver. Here's the schematic of the mixer in preparation for translation analysis through simulation. Here's the simulated signal wherein the input signal of 1000 MHz had been downconverted to a corresponding output of 868 MHz. This can now be analyzed by the second receiver. Here's the conversion gain of the mixer whilst translating signals from 961 MHz to 4000 MHz. The negative value signifies it as a loss. It is consistently close to the typical performance characteristic of the actual mixer. Here's the typical performance characteristics of the actual physical mixer. After seeing the mixer operate, the complete setup of the proposed device had been designed for analysis. Here's the schematic diagram. Here's the simulated signal wherein the input signal of 1000 MHz had been downconverted by the mixer to a corresponding output of 868 MHz and had been received by the second receiver of the device. Here's the corresponding loss experienced by the proposed spectrum analyzer once the signal enters the RF switch, the mixer, then the receiver. Since the receiver of the device can measure signals from 240 MHz to 960 MHz, frequencies from 961 MHz up to 4 GHz will be translated by the mixer to a frequency that is within the range of the receiver. This frequency is chosen to be a constant 868 MHz. This had been simulated using frequency sweep with the corresponding LO as seen above. There are different parameters in the simulations that are significant. These are shown here. The spectrum analyzers N9322C and FSP7 had about 0.82 dB and 2 dB signal strength difference respectively. In the simulation, the mixer experiences conversion gain or loss. This contributes to the overall gain or loss experienced by the device, which is about -8 dB. The displayed average noise level in the simulation is limited to -150 dBm. N9322C and FSP7 have around -146 dBm and -152 dBm respectively. In conclusion, the researcher had been able to design and develop a simulated version through ADS of an affordable, low-cost portable wideband RF spectrum analyzer with extended bandwidth using mixer integration that can handle and detect frequencies from 240 MHz up to 4 GHz. The wideband receiver originally can detect frequencies from 240 MHz to 960 MHz. As seen in slide 35, an input signal of 1000 MHz had been downconverted to 868 MHz, which is frequency within the range measurable by the receiver with acceptable diminution. A simulated frequency sweep of the remaining frequencies of interest, which is above 960 MHz up to 4000 MHz, had been shown in slide 37. The accuracy of the complete proposed spectrum analyzer had been quantified through harmonic balance simulation of the single-tone FFT input and output signal with swept RF frequency for gain loss shown in slides 35 and 36. The device's sensitivity for different frequency had been evaluated by specifically determining the behavior of power level over a certain frequency range through the S parameter simulation of the spectrum S11 and S22 shown in slides 28 and 29, which can be interpreted that the lower the spectrum goes below 0 dB, the better its radiation is, and the closer it is to 0 dB, the more the power is being reflected until it reaches 0 dB wherein no radiation happens. That concludes my presentation. Thank you very much for listening.